Okay, so welcome back, and today we're going to introduce another definition of a discontinuity in the middle of an interval. Okay, so we're going to integrate a discontinuous integrand, meaning that what if there's a discontinuity somewhere along the range of integration? Okay, so we're going to treat it very similarly. It's very similar to what we did with an infinite discontinuity, okay, or not an infinite discontinuity, but as the integrand goes off to infinity, okay. So in this case, we have something like this, where we have this discontinuity, let's say an asymptote usually, or a hole in the graph, and so it's continuous everywhere except at this one point on the interval. And so here it's going to be at B. And so what we're saying is that it's continuous everywhere else. So we can find the area under the curve from A to T. In fact, we can keep pushing T closer and closer and closer to B, and we're fine. It's just at the end point where it shoots off to infinity. And we can't find the interval of or the integration of that. So what we do is we're going to take a limit. Same thing that we did. Instead of taking T out to infinity, we're taking T to a certain point, to where the limit as it approaches that discontinuity. So that's what we're going to do. So if the limit exists, right, so again, we're going to take it to this, and so we're going to take the limit of the integral as T approaches B. Or if it's on this side, we're going to do the limit as T approaches A. Or if it's somewhere in the middle of the interval, then we're going to split it up into two integrals. Okay? So that's what the definition here is doing. Okay? So 1 gives us the first case. Let f be continuous over this interval. So from A to B, but not including B. So let's say there's a discontinuity at B, which is this situation. Then we're going to rewrite the integral with a limit. But this time we're going to take T as T approaches B from the left, right? So we're approaching B from the left of the integral from A to T of f of x dx. And then 2 says, okay, well, what if the discontinuity is at A instead of B? Then we're just going to do something similarly, as we're going to rewrite the integral of f of x dx as the limit as T approaches A from the right. That's what the plus and minus mean. So from A from the right, from T to B of f of x dx. And then finally, the third one is if f of x is continuous over the entire interval except at one point, C. And C is in the interval from A to B, somewhere in the interval. Then we're going to split it up into two different intervals. It's going to be from A to B. We're going to write this as the integral from A to C plus the integral from C to B. And again, we're going to treat these two the same way that we would treat in number 1 and 2. Okay? So that's why I didn't write the limits. Okay. Now, this also assumes that these limits exist, right? So provided that these limits exist. Now, if the limits do exist, then we would say that these converge, okay? If the limit doesn't exist, then we would say that these diverge, okay? And likewise, very similar to before, if either one of these integrals diverges, then the whole thing diverges. So both of these have to converge in order for this to converge, okay? Same thing as before, just now applied to a discontinuity in the interval. Okay? We'll do some examples and we'll move forward.